And then screen share. Okay, that should be good. Let's get that out of here. Hide floating meeting controls. Okay, I'll just wait another minute or two, just in case people come in. Let's see. Maybe full screen. Yeah.
So the tables are full again.
Are they really?
Yeah.
What is going on?
I don't know.
Yeah,
So,
I guess join with Matt. But yeah, I guess.
Did you just like find somewhere?
Yeah, I guess Matt doesn't have a partner. I think is Michael usually your partner?
Yeah, he usually comes a little late.
He's missing today. He's missing today.
Oh, okay.
Yeah, he emailed me.
All right. So you don't mind if I, like,
Yeah, go ahead.
All right, so it's full in the other room. So
Yeah. So I guess I'll.
yeah, that's weird. It's definitely like the case that like someone's friend is in the other one, and they're just like they're like, oh, cool, we have the same TA. Okay, so I'll get started and talk about something that I found weird when I first looked at the lab was that like our first lab in this whole class was electric fields and like what they look like, you know, using them on that thing. And you can do a similar thing with magnetic fields, but I don't know why we're kind of skipping that. We're going right to magnetic force instead of magnetic field. So I wanted to just explain a little bit what the magnetic field for our system looks like. So unlike, I mean, it is very similar to the electric dipole in the sense that kind of negative charges and positive charges elicit these kind of behaviors where the field lines come out of the positive and go into the negative. Now, the difference is that there can be just this negative charge or thus just this positive charge. And that's, you know, a fundamental unit of like something that creates an electric field. It can just be one. It can just be one, you know, plus or minus charge. However, in magnetism, we cannot have just a south pole, for instance, or just a north pole. Sorry, yeah, we can probably, no, it's actually full. So I guess we can just make either a group of three or I can help. Yeah. Yeah, I mean, it's very weird that like it's one room is full, one weekend is, you know, not full the other week. So similarly, we have like instead of negative poles and positive poles, we have what's called north poles and south poles. So the kind of prescription here is that outside the field, so outside this region of magnetism. So when I say magnetism, it's kind of like instead of a point charge, you have like kind of I don't know, an arrow. Like the arrow is your smallest unit of thing in magnetism, where it's just kind of a vector. It points from south to north. Let's see. And I think, what if can I do that? Can everyone still hear me? I guess in the other room? I know everyone in this room can hear me. I just, yeah, probably. Let's see. Probably, okay. So the kind of like the reason why this magnetic field line is pointing in here is because there's some magnetization inside this material. Whereas here it's just, you know, for us it's air, but you can think of it as like the vacuum. There's no magnetic, there's no magnets out in this space around the magnet. So then it just follows kind of the same prescription as, you know, field lines go into the minus and out of the plus, like a plus and a minus. But inside we have this magnetization. So that's basically what the magnetic field inside our, you know, our system looks like. So now after that kind of intro to magnetic fields, I want to talk about, because the equations as usual in lab, they just kind of throw them at you. And this time they're, you know, kind of cool how they derive them. This one is still a little fishy to me. I'm deriving YF equals I WB. And the reason I say it's fishy is the first step I make is I go from this thing, which you may have seen in class. Like it's kind of like F equals ma, but for charges. So this equation reads: if you have a charge q and it's moving in the direction v, you use the cross product. So for instance, if you point your fingers in the direction of v and curl your fingers in the direction of the B field that the charge Q is moving through, your thumb is the direction of the force. So this from hyperphysics, this is where I learned this. I can probably find, if anyone's interested, I'll find like a more rigorous derivation, but this was the easiest one I could find. So you know the reason I say it's a little fishy is because the V that I'm substituting with length over time, I mean, it should really be a rate like dl over dt instead of like L over T. And similarly here, I make this substitution that the current is the charge over the time interval. And that's still true, but it's more formal if I do it as a rate of change. But for our purposes, we can just say that the velocity is a length over time. I can take this little time over here, put it underneath the q, make it a current, and now I have this equation. So now if I look at my setup, if I look at like either the figure in the lab or my actual setup at the lab, I have this string coming down, and you know somewhere in the middle there's this bar with a magnetic field, and so I'm going to define my L as this length going down my string. And here is the string when it's moved. So this is like the equilibrium position of my string. So my L vector is pointing down, and my B vector, which is the field due to the magnet in there, right, is pointing to the right. So then I have this kind of setup. And now I can use that formula that maybe you recognize from calculus or something like that, where if you take the cross product of two vectors, you can write them as their magnitudes and the sign of the angle between the two. So in this special case, I have something going exactly to the right and something going exactly down. So it's sine of 90 degrees, which is just 1. So I can simplify this equation to I and the absolute values of L and B. And then I'm just using the definition from the lab manual that the width of my magnet, actually this is a practical point. The width is the top to bottom. That's what they mean in the lab manual by width. I saw some people measuring the width side to side. So yeah, width is top to bottom. And so I'm just substituting that in with the absolute value of L here to get this equation they have. And now with this, we use a little bit more geometry. This one's a little bit more non-trivial. Whoa, what just happened? Why am I viewing? Okay, that's better. It was like viewing two continuous pages right there. So now I'm going to try to derive this thing for us. Where does this equation come from? So what are these symbols here? The D is from the equilibrium position to where the string stretches out to due to the magnetic field. So it kind of looks like this. And the length of our string is L. So if I divide it in half, it's like L over 2. We'll get to that in a second. So if I think about just a force diagram, I have the string being pulled down by this mass that we hang at the bottom. So there's a tension this way. And because there's this kind of like pivot point, the magnetic field is pulling in this direction because we saw on the previous page that it's in that direction, in the direction of the B field. And I also have a tension exactly equal to this one pulling up towards the support point, I guess, of the string. Now I'm going to use one of those equations we used from 133 last semester, that the sum of the forces has to equal 0. So these two are in the left direction, this one is in the right direction, and I'm going to set them equal to each other. More specifically, I'm only going to look at the x component. So this is purely x. So I'm going to change these two FTs for F tension and F magnetic field into just the x component. And the way I do that is I look at this kind of piece of geometry here. I have the angle. I know this part, but I want this part. So how do I do that? I look at all my possible relationships. I have sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. And if I plug this one in, the opposite of my theta angle that I'm given is what I'm looking for. So then I rearrange this equation with the hypotenuse being this long side here. And then I have the force in the x direction is equal to the force along that diagonal times the sine of the angle. And remember, I have two of them. So I have the force of the tension going up and the force of the tension going down. So my kind of sum of the forces equals 0 is written as 2ft, because I have both of those arrows, sine theta, equals fb. So the one going in the right and the two going in the left. Now, some more tricky geometry. I'm going to assume, and if you look at your lab setup, it's kind of reasonable that we do this. The amount that the string is pushed over is very small. If you look at your ruler, it's a few centimeters. So I'm going to assume that my angle up here that kind of tells me how far away I am from the equilibrium is small. And then I'm going to use things called the small angle approximation. We used it with like the pendulum for 133. More formally, it's called like a Taylor expansion, where the sine theta is actually equal to theta. Oh, I didn't write this down. We don't use it here, but it's 1 minus 1/2 theta squared, I think is the first two terms in the cos one. But anyway, the two that we use are that sine theta is equal to theta and tan theta is equal to theta. The first thing we're going to use is that sine theta is equal to theta. So this equation, using the small angle approximation, becomes this thing. Figuring out what theta is requires another one of these trig identities. If I look at what my geometry is, remember that I said the whole length of the string is L, so half of it is L over 2. And then I have the displacement, which is from its equilibrium position to where it's pulled out to by the magnet, is D. So then if I look at my tan theta trig equation, I have the opposite over the adjacent. I have that, D over L over 2. Bring the 2 to the numerator. And using this small angle again, I know that tan theta is approximately equal to theta. So now I have a value for theta. And then I plug it into this equation. And remember that Ft is just the tension. So it's just the mass and the gravity pulling this down. It's just, gravitational force. So then I plug in my theta, 2d over L. I plug in my tension force, mg. And I plug in what we derived earlier, on the last page, that F is equal to IWB. And then I just, rearrange some algebra. Sorry. So the L goes over to the right-hand side. The 4mg goes to the bottom. And I have the equation that we need to use in the lab. One equation that I don't think should be in the lab manual is right after that equation. It kind of tells you something about the fact that you're, not at your equilibrium. So you're actually measuring, D is x minus x naught. You can completely ignore that equation. I don't know why it's there. And the reason I say you can ignore it is because you'll read in the procedure that you are actually measuring whatever your wire is at now with no, with just the mass hanging on it and no magnetic field, you're already taking that into account. So it tells you on your Excel sheet to write that down. Like when I is 0, what's your x value? So you've already taken this into account. So I don't know why the lab manual asks you to do that, but it's totally sufficient to just use the D, which is also like they also call it X. You can call it X or D. I think in the Excel it says, or the Google Sheet it says X. And you can use this equation here, which hint hint is like a y equals mx plus b equation. Also, it doesn't tell you explicitly in the lab manual what like a good answer is. If you hover over, one of those like ones or twos in the thing where it's like, there's a one superscript here, and then you have to like hover over it. It mentions like 0.3, anywhere from 0.25 to 0.5 Teslas I was seeing Monday, and those were all like everyone was doing everything correctly. So if you get in those regions, it's good. The issue is you need to know what units to do things in if you want to get things in Teslas. So the lab manual doesn't really tell you what to measure things in. To me, it made the most sense to do grams and centimeters or millimeters. But if you want things in Teslas, that's actually an SI unit. So if you want to get B from your slope in terms of Teslas, you need to record your mass in kilograms. You need to record the length of your string, the width of your magnet. Remember, that's top to bottom, and your X or D, whatever you want to call it, in meters. And this one's pretty easy. Your voltage supply / current supply will already give you amps. And then I just wanted to do one last reminder about uncertainties. I found some people were struggling with like combining, like when you have something like this. So for instance, the value you'll solve for your B is 4 mg, the slope from this equation, over LW. If you have something like this, I just want to walk through like why you can do equations 9. So 9 is for multiplication and 10 is for division. You can do them at the same time. If you notice both of those equations in the error analysis PDF, they have, you pull something out and do the absolute value, and then you do the exact same thing in the square root. So if you have, m slope, and sorry, here I just pull out the g and the 4 because those two things are constant, so I just pull them out and I do the uncertainty of the remaining quantities, m slope L W. I can just do 9 and 10 at the same time. So I take the absolute values and then I just do the square root of 4 terms instead of 2 terms. Like A, B is usually just 2 terms. Well, now I can just do all 4 terms. So that's it in terms of theory. I will write something on the board really quickly that I didn't write down here about like using your power supply as a current supply. It's actually very confusing to me, and I asked around and I still don't quite understand it. So I'm just going to tell you what I was told on the board. I'll come over to the other class in just a minute. Okay, stopping share. Does anyone have any questions so far that I'll answer for both classes? And of course, I'll post this recording to Blackboard in case it was too fast. But does anyone have any questions before we get started? If not, I will stop the recording and come to the other class after this one. Stop recording.